Alright, so for our next video, we're looking at evaluating limits algebraically. So the previous videos that you hopefully watched kind of went through what a limit is. We went through how we evaluate limits with a table. And we're going to see that just real quick here again. But now we're going to look at how to do these without a table. So let's get a problem up here. And so, poof, like magic, there we go. There is our limit. Limit as x approaches -3 of x squared plus x minus 6 over x plus 3. The way that we want to evaluate limits, and I don't think I mentioned this in the previous video, and I didn't, because in the way we would do limits in the previous video, we would be doing a table. But we usually don't do a table. Table's kind of the last resort. Think of it like when you were graphing lines. Remember when you first started graphing lines, you made an XY table and you plugged in those values. Now you don't graph lines like that anymore, right? You use y equals mx plus b, you use other tricks. It's kind of the same thing here. The fallback is do the table. The table will always get you the limit, if the limit does exist, and there are times where the limit won't. We'll see that in the future. The table is just kind of a fallback. It's not the best tool. What we want to do is, the first thing we want to do is hope that, and I mentioned this in one of the previous videos, hope that -3 actually works. If we plug in -3 and we get an answer of 7 over 5, that's the limit. We're done. We don't have to worry about a table at all. Unfortunately, when I plug in -3, and I'm just going to do that off here to the side, if we look at f of -3, -3 squared plus -3 plus 6 in our numerator works out to be 0. In the denominator, -3 plus 3 also works out to be 0. That's bad news. A 0 in the numerator is fine. If I get 0 over 7, the answer is 0, and 0 is a fine number. It's when we get anything divided by 0, that's bad news. Really, it's when we get 0 divided by 0. You're going to look at this more in depth next year when you do calculus. But when you get 0 over 0, that's the news that kind of tells you, hey, you're going to have to break this down in some other fashion. Usually, and I'm going to actually go on a limb and say always, at least for us, when you get 0 over 0, your answer is going to be some number. It's just going to require you to do some work to get that number. Now, we could do a table, and if you do a table, it's pretty easy to see what that limit is. Let me put that table up here for you. Alright, and like magic, there's the table. So notice when we're looking at this table, I didn't make the table too in depth, -3.02, -3.01, just like in the previous videos. If we look at the pattern from either direction, the pattern from the top of the table looks like that the next number in that pattern would just be -5. If we look at the pattern from the bottom of the table, working our way up, it also looks like it would be -5. And so that is the limit. The table's not going to lie to you. It's not like the table would tell us one thing and then we do the work and get something else. The answer is -5. The table tells us that. The problem is, what happens if you don't have a calculator where you can create the table quickly? What if the function is really, really nasty? This function isn't bad, but do you really want to plug -3.02 in for x and work that out by hand without a calculator? I don't. And so we have other ways that we could do this instead. It requires work, but it's much faster work, in my opinion, as we work through these more and more and more. In the beginning it might be slow, but it will go quicker. What we're going to do is we're going to look at the limit. So let me rewrite the limit down here next to the table again. That table is kind of gone. We don't need to worry about the table, but I want to keep it up there just so we know what the answer is. So let's get the limit here again. There we go. There's our limit. Now, in math, it is never a bad thing to be able to manipulate an equation. You're always allowed to move things around if you need to. And in this equation, we can totally manipulate this by factoring it. What you can't do is you can't change the function. So I couldn't add 7 to the function. That's changing it. I couldn't multiply by 3. I couldn't square it. I couldn't take a square root. None of that applies. But I can factor things. I can reduce things. I can multiply by 1, and we can go creative ones like multiplying by conjugates in the numerator and denominator and things like that. All these things we're going to see. So I'm allowed to manipulate this thing this equation as long as I don't change it. So how am I going to manipulate it? Well, I'm going to factor the numerator because I know that the numerator factors, and that doesn't change anything. Now notice I'm still writing limit as x approaches -3. That is an operation. If you don't write it there, it's like not writing a square root when you need it. You have to write it every time until you actually do the limit. My denominator, I'm not going to change at all, so I'm going to leave as x plus 3. But in the numerator, I'm going to factor x squared plus x minus 6. Your factoring skills need to be on point. It's old school stuff, and that factors into x plus 3 times x minus 2. what we see is we look at and go, hey, those x plus 3's will reduce. Now, reducing actually changes a function, but it changes it on a very minimal scale, and it changes it really only at one spot, and so this is allowed to do. We can reduce that x plus 3 and x plus 3. I'm going to go through what that just did as far as the graph is concerned, because it did change the function, but not in any way that's going to mess us up, and so we're still totally allowed to do this. And so now we're looking at the limit. Notice I'm still writing limit because I haven't taken the limit yet. All I did was cancel a couple of things out, and now we're just looking at the limit as x approaches negative 3 of x minus 2. X minus 2 is not the same function as the original. This one. They're not the same, but they are really, 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 let's throw one more in, really similar. See, their graphs look like this. I'm going to do one in yellow, and I'll do one in blue. So the one in yellow that I've highlighted in yellow, that graph looks like this. Let's see, negative 3 I'm going to put right about there. So that's the yellow graph. Okay, that graph has a hole at negative 3. That's what this x value is right there. That's x equals negative 3. There is a hole in the graph. Otherwise, it's just a line. The blue graph looks like this. Amazing. That's what the blue graph looks like. So let me pull that blue graph off again. There's the yellow graph. There's the blue graph. Yellow, blue, yellow, blue, yellow, blue, yellow, blue. I could do this all day, but I won't. So the yellow graph and the blue graph are identical in every way, shape, and form except at x equals negative 3. At x equals negative 3, the yellow graph has a hole in it where the blue graph doesn't. Otherwise, they're identical in every other spot, and that's why we're allowed to do this. This is what happens when you cancel things. You change just one little spot, but that one little spot really doesn't matter. And so, now I can evaluate the limit as x approaches negative 3 by simply just plugging negative 3 into the function. Notice what I didn't write here. I did not write the limit anymore. When I plug in the number, I'm doing the operation. It's like now I've taken the square root, so I don't need the square root symbol anymore. Or I've added things together, so I don't need the plus sign anymore, right? If I do 5 plus 3, I don't write 8 plus, I just write 8. The plus sign disappears because I've done the operation. I plugged in negative 3, so I've done the operation of a limit, and so I don't need the word limit there anymore, and I shouldn't put it there. And negative 3 minus 2 is equal to negative 5, which is the exact answer we thought we would get when we looked at the table. But I didn't have to do a table to do this. All I had to do was factor. Now, this is one way to evaluate limits. This is one tool you have in a very big tool belt that you've been building since kindergarten, with all the math knowledge that you've learned, and even before kindergarten when you were just learning stuff on your own. All of those tools are still available, and all of those tools you may still need to use, and we're going to see a few of them in the next couple examples. So let's move over to the next slide and see what the next example is going to bring us. Alright, so for this example, we're looking at the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. Again, the first thing that you should do every single time is try plugging in that number. If I plug in 0, I get 0 plus 1 underneath the radical, which is just 1. The square root of 1 is 1. 1 minus 1 is 0, so we have a 0 in the numerator. And I plug in 0 in the denominator, I have a 0 in the denominator, and I get 0 divided by 0. Anytime you get 0 divided by 0, that means you're going to be playing around with the function in some fashion. In the last example, you factored it. Doesn't mean you're always going to factor. There's lots of tools that you have in your tool belt to manipulate equations, but again, you have to be careful. You can only manipulate without changing them. Now, we could make a table with this and set up a table and find the limit that way, but instead we're just going to do some algebra. So here's what I'm going to do to figure out what this limit is. Now, how do I know what to do? Well, I've been teaching math for over 20 years. I've seen this stuff for a long time. I have a lot of experience. You will get that experience as well. What happens is in math, we do something and it works, right? And then we see something else and say, hey, this looks similar. Let's try what we did before, and it works again, and we go, cool. And if it doesn't work, then we just try something else. You have the benefit of me that knows the correct path, so we just jump right to the correct path instead of trying like 20 different paths, failing every time until we get to the right path. You will get there as well through practice. So what I'm going to do is I'm going to multiply the numerator and the denominator by the conjugate of the numerator. This is weird because usually we would never do this. We would multiply a denominator by a conjugate in order to have no more radical in the denominator, but that's not what we're working on here, and you can multiply by any conjugate you want. I could actually multiply the numerator denominator by anything I want, as long as I multiply by the same thing. Why? Because this fraction right here, that's actually just equal to 1. And so I'm allowed to multiply by that fraction because I'm really just multiplying by 1, which means I'm not changing anything. Now, we want to make sure and think about how this multiplies. These are technically in parentheses. When we multiply conjugates, it's important that you remember how to multiply those. Now, to save yourself some time, you could just multiply them all through, meaning distribute the square root of x plus 1 through and then distribute the negative 1. But if you remember what happens with conjugates you only have to multiply the first and the last product. The other two products that you would get would actually cancel out because they would be the exact same thing, just opposites. So when I do that multiplication, the square root of x plus 1 times the square root of x plus 1 is x plus 1. When I do the second multiplication, a negative 1 times 1 is negative 1. And so there is the numerator of our fraction. The denominator of our fraction, this is technically in parentheses as well. We're just going to leave that. Never, ever, ever multiply out a denominator. It's never going to help you. Just leave it just like that. You'll see why in a minute. So I haven't changed the function. These two functions, the original function and what I have now, are exactly the same. All I did is multiply it by 1. If I multiply something by 1, it's not changing anything. And so now I can clean this thing up. We're looking at the limit as x approaches 0. In the numerator, 1 minus 1 is 0, so I just get an x. In the denominator, I have x and then parentheses x, the square root of x plus 1 plus 1. And notice what happens. My x's cancel out. That's kind of the whole purpose of most of the problems you're going to do. You're looking for things to cross out. And so once those x's cross out, I end up now with the limit as x approaches 0. Notice I'm still writing that because until I plug 0 into the function, I have not taken the limit, and I need to continue to write that there. And so now I have 1 over the square root of x plus 1 doesn't need to be in parentheses anymore. Now I can go ahead and plug in 0, and when I plug in 0, I get 1 over the square root of 0 plus 1 plus 1. Notice I didn't write the word limit anymore, because when I plug in the number, I'm taking the limit. And that gives me 1 over the square root of 1, which is 1, and 1 plus 1 is 2. I get an answer of 1/2. That is the limit. That's the limit we would see if we actually did a table, but notice I didn't have to do a table for any of that. Okay? So now we're going to take a look at one more quick example, and then we'll be good to go. And poof, like magic, our last example. We have this limit as x approaches 2. We got some fractions and fractions. And so this is another skill that I want to make sure that we have down. If you try plugging in 2, hopefully you'll see that you'll have in the numerator 1/2 minus 1/2, which is 0, and then the denominator 2 minus 2 is 0. So I can't just plug in 2, so I have to manipulate this thing. There are lots of ways to manipulate this thing. Lots of things you could do. Me, I'm a big fan of getting rid of fractions completely. I can't do that, but I can at least get rid of the fraction that's in the fraction. And the way that we would do that is find a common denominator for all the things that you have. Now, x minus 2 doesn't have any denominators that I care about, but the numerator has a 2 and an x as its denominator. So what I'm going to do is multiply everything by a 2 and an x. Whatever the denominators are, I multiply by the denominators. This will make all of the fractions in the fractions go away and leave me with just one single solitary fraction. And so when I do that, I still have the limit. I haven't taken the limit yet. In the numerator, if you distribute that 2x, the x's will reduce in that first fraction, and you'll end up with 2. Minus, if you multiply 1/2 times 2x, you just get x. The denominator we would never multiply out, so leave it just like that. Now notice, our goal, as I mentioned in the last example, is to get something to cancel, and nothing cancels here yet. But the numerator and denominator are really close. What I can do is I can factor a -1 out of the numerator. That's going to change the sign of x and going to change the sign of 2. If you were to distribute that -1, that would put you right back where you were. So again, all I did is factor. I didn't change anything. But now, notice what happens. My x minus 2's cross out, and I'm allowed to do that even though it changes the function. We talked about that earlier. And so that's going to leave me with the limit as x approaches 2. Of -1 over 2x, and now I can plug in 2, and I get -1/4. All right? So you have a lot of tools in your tool belt. You're going to have to play around with a lot of these things. These are 3 common ones. There are other things that you may end up looking at. We haven't looked at any trig yet. Those things could cause you problems in the future. So we just have to make sure that we're skilled at all of the things we've been taught before. And some of that stuff, it's been a while. And so that's going to have to be something that we might have to look up. But in the end, we're able to break these things down and find these limits without tables. But if we can't, we always have the table to fall back on. In our next video, we're going to get some homework. So until then, stay safe and stay healthy, and I can't wait to see you soon.